Hey everyone, welcome to my talk, Dirty Vanity, a new approach to code injection and EDR bypass. My name is Eliran Nissan. I'm a security researcher at Deep Instinct. This is my Twitter handle if anybody would want to contact me after the session. A bit about my background. I started around 10 years ago as a security researcher in IDF, forensic researcher, and then I moved along to the realms of research in both the offensive and defensive side. But my main forte and what I like to do is the defensive side. I like solving security issues and Windows internals, and I don't like cybercrime or lactose. I'm sensitive, so please none of these in this session. So a bit of overview. The goal of my session is to showcase Dirty Vanity, a new injection technique that abuses forking, which is a mechanism for process creation in Linux, but it's lesser known to be existing in Windows as well. Before we'll dive into Dirty Vanity, we'll lay some foundations, starting off with forking background, a bit of forking in Windows and why it's there, API to invoke it, the internals behind those forking mechanisms, and we'll go to Dirty Vanity finally. So starting off. Forking background. So forking is the act of creating a new process from the calling process. I bet a lot of you know this. It originates from the Unix system calls of process creation, fork, and execute. In this example here, we have parent that will issue a fork call, and this will create an identical child that will resume its execution just after the fork's return. And then the parent as well will resume execution after the fork. What will differentiate between the parent and the child that are identical is the return code. Here, the return code will be 0 for the child, it will symbolize the child's execution. To, in this example, execute an exec call to replace its image. And the parent will execute on a different return code on the else branch. Okay, so most of you maybe know this. So the origins of the Windows fork. So Windows doesn't use fork and execute for process creation, but it did support it with its legacy POSIX subsystem, a subsystem that it's intended to support basic Unix binary execution. In this subsystem is included the PS6 DLL, which exports basic Unix API, and among them, this fork snippet, or the fork, to support Unix runtime. And we can see that internally, it's implemented with a call to RTL clone user process and anti-DLL export. We'll dive into it later, but this is how the fork is introduced into Windows. So a bit of mechanisms nowadays that use fork in Windows. First one is process reflection. The goal of process reflection is to allow analysis on processes that should constantly provide service. And why is this an issue? Why is this a need? Let's take, for example, this debugger here. And let's say it wants to debug service exe that provides some crucial service to the operation system's runtime. If debugger will resume to debug this process, it will render the service unable to provide service and then disrupt the system. So what reflection does is it allows us to fork the said process to be analyzed, and then we can analyze the suspended fork without interrupting the system. How it's work is, this is the component in Windows that uses it, WDI, Windows Diagnostic Infrastructure, that makes use of process reflection to do such things. In this example, WDI, instead of debugging service directly, will issue a call of RTL create process reflection that internally causes service to fork itself and will create a clone service. Then WDI can resume to debug this process or do whatever, dump its memory. Okay, another mechanism, a bit more well-known one, is process snapshotting. Another mechanism similar to the last one that allows us to query data from process, states, and memory data, but it does so, this is a description from MSDN, using the Windows internal POSIX for clone capability, the one that we just covered. The API name that invokes it is PSS capture snapshot. Okay, our next example of forking involves the credential defense realm. Let's cover a basic credential attack and credential defense. In it, we have the LSAS process that contains the OS credentials. And an attackers would usually want to read it using, let's say, minidump, write dump, or other reading APIs. And then EDRs for see this and protect these attempts. Forking is introduced to credential theft. It's a known example of abuse of forking. And in it, instead of reading LSAS directly, the attacker will issue a snapshot or reflection API, which is underlying implemented with a fork, to clone LSAS. And then the attacker could then proceed to do a mini-dump or read of the LSAS clone, which will leave the EDR unaware. Some of the EDRs don't attempt to foresee this. So we moved along basic lines of forking usages and abuse and a common abuse in Windows. let's go into forking internals. The forking has, as we saw, has a point of power in the system and can allow us to manipulate the system. Before diving into forking internals, let's distinguish between two forking types, the self-fork and the remote fork. So in the self-fork, a process will request the kernel to fork itself, causing a fork to be created, which is identical to the process, to the calling process. In a remote fork, which is allowed in Windows, the process can request from the kernel to fork a different process, the target process, which is done in the reflection snapshotting mechanisms, and then the kernel will create a target clone for the process. And the target clone will be considered the target's child. Okay. Starting off with the first fork API that we've seen, the RTL clone user process, the self-fork that implements the Unix fork in PS6DLL, contains a regular set of parameters, and when issuing it, it will clone the calling process. Let's see how it's actually implemented in NTDLL. This is its code, basic acquiring of locks at the beginning of its runtime, and then calling a wrapper to RTLP create user process, a wrapper to NT create user process. The syscall to create processes in Windows, which traditionally points to a section handle, a file, and creates a process from it, but when given the correct parameters, it will create a process from a parent process handle. After the API executes, RTL clone user process uses the return code. In Windows, 297 signifies child handling, and the child code will be handled in this if condition. And on a 0 return code status success, the parent will be managed. Okay, this is how the actual anti-create user process syscall looks and what creates the actual fork. And the parameter that's responsible to it is attribute list, PPS attribute list. And when populated with the correct way, it will clone the calling process. We create the attribute list and populate it with a PS attribute parent process. This is how Windows treats processes to be cloned. And if we set its value PTR to get the current process handle and set these arguments to the anti-create user process syscall, this will clone the calling process. But what I want to see, because I want to see if this is capable of forking a remote process, because this is the stronger way to manipulate the system. So I want to check if this is possible, if I can set a remote different process handle to the calling process. So let's see what I did to examine this. I created forker.exe just to use this to clone an Explorer exe, and issued the call with attributes that point into the Explorer parent, and I got this status invalid parameter in Windows that signifies something went wrong. So I want to see if something went wrong because of this is an API limitation or something I wrote wrong in my code. So let's debug this in WinDBG. Okay, I'll put a breakpoint in the kernel side of anti-create user process. And this is a large function, so I don't want to step in every assembly execution line, but I want to see where this return code of status invalid parameter originates. Okay, so I'll take the call stack, and I'll see the return address from this function, and then I'll issue this command, PIR, to step through each and every assembly line of execution of this function, and I'll see where this return code of status invalid parameter originates. I can see that finally it returns it in the REX register. But in order to find why it's originating, I will search the entire output for this value, and I can see the address in which it's originating. And I can see the reason why it's originating. Because of a comparison between two registers, R13 and RCX, I can get the values from the trace. I see because they are not equal, the value is being assigned. So it looks like the API is intended to do this. These values are eProcess values. I'm not showing it here, but it can be seen with the disassembly. But when I'm checking these eProcess values, I can see that they point to the Explorer that I'm trying to clone and my own calling process. So this API is limited to a local fork, not good for remote forking means. So how is the remote forking working? Because remote fork can execute in Windows. So I'll examine the known working mechanisms. Snapshotting, starting off with snapshotting. In order to invoke a remote fork with snapshotting, I'll point it to a process handle to fork it, to create a snapshot of it. And underlyingly, it points to PSS anti-capsule snapshot of NTDLL that redirects to anti-create process EX, an older sibling of anti-create user process, an older system call for process creation. But this one can actually fork a remote process. How? It's very simple. We can see here both anti-create process EX and its even older sibling, anti-create process, can be pointed to a parent process, simple as that. And then when we'll provide this argument and put a null section handle, we'll get a fork of the calling, we get a fork of for process to our liking. This is how the parameters need to be set, process to be forked to be inputted here, and nulls for the section handle. And this will fork a remote process. Okay, on to the next remote forking mechanism. We've covered reflection. So reflection has an even more interesting signature. It can be guided to a process to fork, process handle, and then it has two extra parameters that are interesting, start routine and start context, meaning I can start a fork from a location of my liking, with a limitation that we'll examine, and a context, a parameter to be executed, to be inserted to the routine. So this is interesting to me. So let's dive into the reflection mechanism and see how it's actually implemented in Windows. This is a flow chart of the reflection mechanism, of the reflection API flow, but I'm going to guide you through each step. First, we have in this example reflection requester that will request a reflection to be made on the target process. Reflection requester will issue a call of RTL create process that will execute over the target with the target handle. And for the first step, it will allocate a parameter block and will map it to the target memory space. And for the second phase, it will invoke a call to RTLP create user thread, which is a wrapper to create remote thread, that will work over the target with a starting entry point inside NTDLL, a stub called RTLP process reflection startup, meaning the entry point to a reflection. So this thread will execute this entry point with the shared parameters that are mapped to the target, and it will cause it to actually invoke a local call to RTL clone user process, the local mechanism to request a fork in this case. And as we've covered, this will call to the RTL to anti-create user process. The system called it forks a local calling process. Let's check how it's looking in the kernel side of things. The kernel side of things looks pretty similar, starting off with the kernel side of anti-create user process, moving along to PSP allocate process for process creation in the kernel, but things start to get different when moving to this API, initialize process address space. And this time around, the Boolean flag that signifies this is a clone operation is being turned on because of the parameters that I've inserted to anti-create user process that points to a parent attribute. And this time around, the function that's being invoked is my clone process address space, which does the actual cloning. It creates a copy on write view of the target process, the process that it's targeted, and assigns it to the newly created process, effectively creating a clone of the process. Okay, this function finishes and returns to the context of anti-create user process in the kernel side, and it returns two status codes: status success to the target that called anti-create user process, and RTL clone child 297 to the newly created target clone, which contains the shared parameters block from the first step of the allocation, meaning shared allocations and other allocations that are created on the target will get cloned as well. So this is very good for me for my intentions. We'll cover them in a bit. So the RTL clone status code is returned, and the fork starts within the startup of RTL process reflection startup just after the call to RTL clone user process. And for the first step of this clone runtime, it sets the parameter in the LDR to shut down in progress to be 1. This is the intentions for this fork. So if we want to cause this process to be more functional, we're going to remember this for later to set this back to 0. And according to the shared parameters block that I've specified, it's going to choose whether to suspend the thread in normal cases to allow it to be analyzed, or to invoke a start routine that I've entered in the calling parameters. So, according to Windows internals, the Bible for Windows internals, start routine must be implemented inside NTDLL context. Okay? So I'm limited. Maybe I cannot write everything I like. This is where I'm going from, and to start executing the fork from it. But so let's check this. Let's check the invocation of the actual start routine in assembly. This is the entry point of the fork entry and how it's being actually invoked, the start routine. Start routine is being pulled in the fork child to RAX and start context to RCX, and then they are being invoked with the call to guard dispatch icall FPTR. which if you know, it's the mechanism of CFG being executed here, CFG being control flow guard. And control flow guard is a defense mechanism that prevents an execution of an invalid address, and it verifies the address to be invoked, in this case start routine, to be a valid address. But what it protects from is memory corruption vulnerabilities. And start routine here is not caused with a memory corruption. It's caused because it's dynamically allocated. And if I allocate it with a page execute on the process to be forked, it will get forked and contain the same permissions. And if I set it with a page execute, CFG will not protect from it. So this is bad, and I can execute every allocated process, every allocated memory from the forked parent, but without limitation from CFG. CFG won't disable me to do this. So I can abuse it. So let's recap what we just covered. We mapped the remote forking methods of anti-create process and RTL create process reflection. Anti-create process and process EX are system calls that are being directed to a remote process, and the kernel will fork them for me completely. And RTL create process reflection will cause the process that I'm targeting to invoke itself, a call to a local fork to be invoked. By focusing on the second method, we gain familiarity with the forking internals, including the kernel side, which is similar to the anti-API of anti-create process and process EX. And we've seen that MI clone process address space does the actual clone and copies the parent's memory as a copy on write view to the child memory. And we established that protection that's supposedly existing on the start address of the fork in the reflection has a flaw that it doesn't protect from dynamic memory addresses that contains execute privilege. So it's time to talk Dirty Vanity. So Dirty Vanity is an injection technique. Okay, so let's cover basic injection and injection defense before doing Dirty Vanity. In injections, we have a couple of necessary primitives: allocation, writing, and execution. Allocation is optional because someone might find an area that's already allocated and write to it, and then execute it. But any other combination, aside from writing and executing, any other combination is not enough to be an injection. If EDRs will try to correlate this, they will get a ton of false positives because only allocating and writing, let's say, is only as a legitimate communication method in Windows. So in this example, we have injector, exe, that will try to inject to Explorer. And from the EDR perspective, EDR monitors events being made on Explorer and events being made from injector, and will try to correlate this being made on the machine. So for simplicity's sake, I've chosen injector to do an allocate primitive of virtual alloc_x, the most simple one, and the EDR notices it and monitors it to itself. When injector will write to the allocated space, the same allocated space that it created, EDR correlates this and monitors this as well. And when injector will wrap things up with an execute primitive, here create remote thread, EDR detects that this injector created an injection on Explorer, Explorer is injected, and will do things its way from now, terminate this, or whatever it chooses. So Dirty Vanity, what Dirty Vanity does differently? Dirty Vanity makes use of the three remote forking APIs that I've shown, RTL, create process reflection, anti-create process, and process EX, and use them as two new primitives of fork or fork and execute. So how it's actually working? In Dirty Vanity, things will start off similar. Injector will allocate space, or can allocate space in its target. And then we'll issue a write primitive. This time I dubbed it the initial write primitive. Why? Because it's not the final write. The write is going to get happened anyway. Again. So this is the initial write just to create the allocation in Explorer in the parent process. And then for my third phase, I'm going to use a forking primitive. For the sake of simplicity of this demo, I'm going to use a fork and execute primitive, RTL create process reflection. And when setting it with a start address to the address that I've allocated on the parent, the same address is going to be allocated on the clone child of Explorer that's now newly created. And when I finish this API call of RTL create process reflection, this Explorer clone will already have my injection up and running, my shellcode already executing inside it. from the EDR perspective, it caught allocation and writing on Explorer, but no execution. It doesn't know the forking primitive, and nothing was ever written to the newly created Explorer by the EDR side. So when it's finally starting to execute an injection, nothing is new here to the EDR. So this is the strength of Dirty Vanity in this side. So some prerequisites. For the fork and execute step, I'm going to need for the RTL create process reflection variant, process VM operation, create thread, and process duplicate handle. And for the anti-create process and process EX variant, I need only process create process permission. And for the initial write step, it can be anything that you can think of. I'm using the write and allocate for simplicity, but it can be section creation and mapping, setting thread context to do ghost writing or anything else exotic that you find. The writing attempts will get cloned to the newly created child. So let's look at a POC of the Dirty Vanity via RTL create process reflection. In it, we have a shellcode here, normal shellcode, and we're going to open a target handle, let's say Explorer, and then we're going to allocate our space on it and write to it on the base address that you got from virtual alloc. For the third step, again, not executing, but forking and executing later, this time around with the fork, executing the base address, and the fork child will execute our injection, our shellcode that we created. So let's test this. My first attempt with it was reflecting a simple MessageBox shellcode. I bet you encountered those. And it invokes a MessageBox A from user32 DLL. When I break in a clone process and resume my execution, I got this disappointing screen of access violation, access denied. So let's check the call stack. I get the access violation from this address, user32 get DPI for current process. And when messing around with the contents of the RAX register, I am getting some invalid address. So I'm checking the call stack here, and I'm seeing I'm still originating from the message box that the fork child actually invoked, but something goes wrong here, so I need to check out why. Okay, so let's starting with disassembling the get DPI for current process and checking what's failing. I can see the RAX register is being pointed to user32 GPSI, a symbol from user32. And when actually reading it later, the contents, we fail. Let's get the address of the actual symbol, what it's pointing to. And from using this command, I get this address here, 210, next. And when I'm checking the contents of the actual address in the fork child, I can see it's actually non-existing. It's a free page. So it's a surprise to me. I thought that the fork should copy the entirety of the memory of the parent. So what happened to this address? So let's check it. Let's try to see why the symbol GPSI is missing. So starting around, I'm going to examine this address on the parent process to see what its features, and maybe it will give me a hint of why it's not getting forked, this address. So the contents of this address is those committed address with a permission of mapped, meaning a shared memory address. Okay. So let's check further, and let's check the GPSI symbol from user32. This is its initialization, and I see that during the boot of user32, this is its DLL main user client DLL initialize. GPSI is pointed to the G shared info symbol. A symbol that points to a shared info structure from kernel that is mapped to every process that loads user32. This structure is a GUI structure that holds session-specific data and GUI handles and all sorts of this stuff. And it resides in a shared read-only section that is mapped from kernel to each process that loads user32. Let's see how it's getting loaded. Okay, process here loads user32. which executes its DLL main, which invokes a call to from Win32U anti-connect process, anti-user connect process, which invokes the kernel side in the Win32K driver anti-user connect process, invoking init map shared section, an informative name that maps the actual shared info object to the address space of process that loads user32 that contains the contents of the shared info structure. So this is the GPSI. This is the contents that I'm missing. I want to check now why, and now I want to check why it's missing. I got my info that I need. So let's check why. My first guess is maybe mem-mapped or shared memory addresses are not getting mapped to my forks. So let's check it. I'm going to check every mem-mapped address in the created fork in my example here. And I'm saying there's a bunch of mem-mapped addresses, including the address that that the reflection demo that I've shown you, the shared parameters are also getting forked. So there is no reason for failure here. So let's check deeper in the kernel implementation of the fork. I'm going to check how the forking process works and why it skips this allocation of the GPSI. Okay, I'm going to start off things with mi clone process address space. As you recall, we took the dive from anti-create user process up to mi clone process address space. And this is the function that does the actual clone from the parent to the child. It receives the e-process of the parent to clone and the e-process of the child to populate. And it invokes this function, mi allocate child VADs. A quick definition of VAD is a kernel object that describes basically an allocation of the process that contains it. And each process has a pointer to a VAD tree, a root of its allocations, and this is how it manages its own allocations. This function, mi allocate child VADs, iterates through the parent process VADs and creates them to the child, but first it applies them with the filter. This filter is mi VAD should be forked. Sounds promising. This function receives every VAD of the parent process and applies the condition to it. And if the condition will be correct, the VAD will get forked. So let's check it. This is the pseudocode of the mi VAD should be forked function, shortened for the sake of simplicity. And for most private VADs, meaning everyday allocations, it's going to return 1. Meaning VAD going to get forked. But in the case of mem-mapped or shared allocation, shared VADs, it's going to test something. It's going to test whether the field here in the VAD, long flags2, the flags2 member in the VAD, it's going to check its 26th bit and if it's set to 1. If it's set to 1, it's going to say this VAD is ready to get forked, else it's going to return no, don't fork this VAD. And we're checking the struct definition of the flags2. I see that the 26th bit is the inherit field. Sounds good, sounds like it's the right way. I want to see if I can set this inherit bit that I'm missing to 1, to yes, inherit this. So let's check what is this inherit bit and how can affect it. Okay, I'll try to Google this. I'll try to check the flags2 inherit. And I get the struct definition from Google. So it's a loop. I am not getting anywhere from Google. So I'll try IDA. I'll convert this flag to its hexadecimal form, this value here. And my aim is to detect usages of it in NTOS kernel. And I want to see how it's getting manipulated and how it's getting inserted to a VAD. And then maybe I can set it myself to this VAD. Okay, so I'll search this string in little endiness in the entire binary of NTOS kernel. When I search this, I get a ton of output, a lot of locations that use this value because it's a very generic value. Some of these places are not even code in my search query. But I can sort it. And if I sort this search query to search only in areas that are mi prefix functions that manages memory in NTOS kernel, and only operations that are not test but move that actually use this flag and set this flag, I found 2 interesting hits. mi map view of image section and mi map view of data section that actually set this value to a newly created allocation. So I'm going to check how. So I'll reverse these two areas. And what I find is this pseudocode. I can see that the inherit flag is being controlled by a Boolean. And this Boolean is being controlled by arguments. If this Boolean is true, this actual flag is going to be set to the newly created VAD. Good for me. Let's see how we can affect it. Let's check what is this argument. I'm going to follow up the call stack from the areas that I found in my map view of image and data section, and following up to anti-map view of section. And I reveal arg6 to be section inherit disposition, parameter of anti-map view of section. Okay? This thing I can check in Google. It's an API. And when I check it, I get that inherit disposition is defined in this way, specifies how the view is to be shared with child processes. The possible values are view share. The view will be mapped into any child processes that are created from this parent process, or view unmap. The view will not get mapped into child processes. Sound like exactly what I'm messing with. And we even have a recommendation from MSDN. Drivers should typically specify view unmap for this parameter. So this is exactly what's happening. GPSI is mapped from kernel space from Win32K driver, and when I check the actual mapping code in Win32K init map shared section, I can see that the shared section is being mapped with a view unmap value. So let's recap things, okay? I try to fork a process, and I wanted to invoke a message box in it. But it used this value, and this value is mapped with view unmap. So, and view unmap sections are not getting copied to the fork child. So this is my shellcode crashed. GPSI is pointing to this section, and the MessageBox shellcode fails. So what are my options now? Okay. There are a couple of options. Some are more difficult than others. I can try to reload user32 DLL, and this way the shared section will get reloaded, invoking the load of the anti-connect user process again. I can copy the contents from the parent of the shared section, from the parent to the clone. And I can even call the API anti-user process connect to remap this shared infrastructure from the fork child. But what I've chosen to do is to write my reflected shellcode with only anti-API. Anti-API are independent. They don't need any other layer of shared memory to support them. By the way, I can use any low-level API from kernel 32, like load library and others. It's a method of try and test, but anti-API works flawlessly. And let's explain also why view unmap is existing here, why the forks are faulty. How it's actually working in the Unix subsystem that's supposed to actually function. So when I'm examining the actual forking code, the actual mapping code of allocations in the POSIX DLLs, I can see that every mapping in the POSIX subsystem uses the view share member, and the view unmap is only a Windows usage value. So this is how the Unix fork works and able to create executing processes, and this is why it's interrupted in Windows. So I'm going to reflect a shellcode anti-API for my demo. My shellcode is going to, instead of creating a message box, invoke a call to anti-create user process, invoking a message, MSG executable that says a hello prompt. And this is what my shellcode is going to do. I'm going to set the contents of the LDR again to shutdown in progress to be 0, because when this is 1, it harms the process runtime, it harms APIs. And I'm going to find my anti-DLL API from the LDR and perform parameter creation for this anti-create user process with RTL create process parameter ZX, and then invoke anti-create user process from the reflected shellcode, invoking CMD and a command line of MSG, hello from Dirty Vanity, and I'm going to suspend it to allow you to see it. Okay, now it's time for the demo. Demo. Okay, we have a demo here of a system that's protected with an EDR, and in it we're going to target Explorer. This is the Explorer process 3. This is its PID. And I'm going to target this PID first with an ordinary injector. And by setting the PID of Explorer 6480, I'm getting my injection working, hello world message, and an EDR prompt down here. The EDR caught this attempt, I censored it. So, because I don't want to mess with anybody. And when the EDR created a new explorer because it contains shellcode, and a new explorer is created, I'm going to invoke Dirty Vanity on it. The prompt is being executed. And when checking the actual process tree, I can see that Explorer indeed created a new Explorer image. And this child Explorer created a CMD that invoked my MessageBox, so the shellcode in NTDLL actually operates. Thank you. OK, so this was the demo. Time for summary and takeaways. To detect injections, EDR solutions usually monitor and correlate attempts of allocation, writing, and execution. It allocates and correlates these attempts on that are being invoked on a single process on the same process. What fork API do is they introduce two new primitives to this injection game, fork and execute. And what it does, it basically splits the EDR's vision. Dirty Vanity makes use of forking to reflect any attempts of allocation and writing to the newly created target process, the child clone process. And from the EDR perspective, the parent was never executed, and the child is never being allocated or written to. And thus, it will never get flagged when eventually I will choose to execute it, either with a fork and execute primitive or forking with the forking APIs, and then finally actually executing it in every other execution primitive that I want to follow up with. And a couple of takeaways for you. Dirty Vanity changes how we look at injection defense, because forking changes how we monitor the system. What EDRs how EDRs should respond is they should monitor all the forking primitives that I presented, eventually tracking forked processes and applying them with all the knowledge of the parent. Dirty Vanity can be used, or the forking can be used in other attacks. We saw an abuse of credential dumping. This is the injection world. And we must apply the entirety of the knowledge of we have on the parent to the child process to prevent these kinds of attacks. And more variations of the Dirty Vanity injections exist, up to you to map them all. We can do the anti-create process or process EX system call with a follow-up execute primitive. We can patch the entry point of the fork to do anything we like. And we can try to fix, it's possible, higher level APIs, but generally NTDLL can do anything that younger brothers can do. Up to you to catch them all the variations. And thank you. This is where I'm finishing. This is the link to the GitHub that contains the POC demo to Dirty Vanity. It contains also the shellcode generation framework that I used that invokes the shellcode of NTDLL API. You can customize it quite easily. This is my Twitter handle if anybody would want to contact me after the session, and some references that I've used. And time for questions if anybody has one.